Hello, everyone. Today we're going to talk about an introduction to mechanics, Xhyn kinematics, and motion graphs. Well, kinematics is, with vectors, the very first topic taught in physics. It's very important because it was uh, discovered by Isaac Newton, very much in detail in his book called Principia of Natural Philosophy, which was the beginning of physics as we know it. Mechanics is commonly the first topic taught in physics since it is a study of motion, forces, and the basic interactions between physical materials. These physical objects may experience forces from collisions or from interactions in space, such as gravity, which exists without objects touching each other, right? So we have in space we have space-time and we have the dimensions, we have the vibrations, and we have fields throughout space, and one of these fields um, generates the force of gravity between objects. Isaac Newton is the inventor or possibly the discoverer of kinematics and the laws of motion that define mechanics. He relied on notes taken from scientists such as Galileo Galilei and Johannes Kepler. Of course, nobody can do anything alone, and on the shoulder of giants we stand to see further into the horizon of an or search for ultimate knowledge, ultimate understanding of everything that there is. Newton, this possibly the most intelligent person in world history, he wrote about motion, forces, momentum, impulse, angular momentum, and gravity. He did also works in optics. He created the world's first reflector telescope, which is a technology used in modern day telescopes that we put in space, such as Hubble telescope is also a reflector telescope. So, um, like I should say that without Newton, we would be much behind in everything in science and technology than we have today. So Newton um, made possibly centuries of progress in his lifetime with his work. Isaac Newton stated the three laws of motion. An object will stay at rest or moving at a constant velocity unless a net force not equal to zero acts on it, law of inertia. So if there are forces on the object, that doesn't mean the object will accelerate because the forces should have a resultant not equal to zero to lead to an acceleration. Or if an object is moving at a constant velocity, it will stay there unless a force, friction, or air resistance slows it down, or unless a force speeds it up. Force equals to mass times acceleration. That's the second law, and every action has an equal and opposite reaction. So when you exert a force on something, that something exerts a force back on you. So when I kick a soccer ball with my foot, the ball goes, my foot stays, but that's because my foot has more mass, and also because there is friction between my shoes and the ground. So, and the ball goes because the ball has less mass. So whenever you have a collision between a truck and a car, and then you say, no, the force of the truck and the car is greater than the car and the truck. No, that's wrong. Even though the car seems more wrecked, that's because the car has less mass. So, but the force is exactly the same, just in opposite directions. Newton also developed the four equations of kinematics, which are set as is. These equations drive the universe. Not really, because in reality, the universe is much more complex. We physicists, we try to simplify things, assuming ideal cases like ignore friction, ignore air resistance, ignore this, ignore that. So these equations are just for our own understanding if we want to run a simulation, a computer, and stuff like that. So we got proofs for the kinematic equations. The first equation we can prove is 1/2 times v initial plus v final times t. Well, the 1/2 plus v initial plus v final, that's average velocity. And then if you multiply velocity times time, you get displacement. Because meters per second times second gives you meters. So if you're going 20 meters per second for 2 seconds, you would have gone 40 meters. Now, if we have the equation Vf equals v initial plus acceleration times time, we know that we can solve this equation for acceleration by doing v initial, v final minus v initial over time. That's acceleration, because acceleration is change in velocity over time. So if there's a change in velocity, there's an acceleration. If there's an acceleration, there's a net force that is not equal to 0. Now another equation we have is delta x, which is the displacement. The triangle symbol is the Greek letter delta. V initial times time plus 1/2 acceleration times time squared. So if we have the equation v final equals v initial plus acceleration times time, and if we plug it in that equation for Vf in the above in equation displacement equals 1/2 v initial plus v final t. If I put the Vf into that first equation, we get this expanded equation, and when we simplify, we get the displacement equals v initial times time plus 1/2 acceleration times time squared. So once again, nothing in physics is a guess. Sure, we do a lot of ideal cases where there are no match to reality, but one thing to understand is that nothing is a guess and everything can be proved mathematically. So we know that in the same way that v final minus v initial over time gives you an acceleration, v final minus v initial over acceleration gives you time. Now, if we insert this equation for time into our equation for displacement, v initial times time plus 1/2 acceleration times time squared, we get that expanded form, and from there, we can, after some algebra, we can reach the equation v final squared equals v initial squared plus 2 acceleration times displacement. So here I've explained all 4 equations of kinematics, which can be proven mathematically. Now another thing we're going to talk about here today is motion graphs, because if you have motion, it's always important to explain what is going on to the object as far as velocity and what changes in position with a graph. So we have position versus time graph, we have velocity versus time graph, and we have acceleration versus time graph. So for an object at rest, the position versus time graph is a flat line above the axis or below or anywhere. So it's a flat line. It could be at 0, it could be anywhere. It means you're not moving. So you're in the same x position, so it's a flat line. Now, so because the object is not moving, that means that the velocity versus time graph is right on the axis, which is 0, and acceleration is also 0. Object at a constant positive velocity, so it's a linear equation on position versus time graph with a positive slope. The slope of a position versus time graph is velocity, and the slope of velocity versus time graph is acceleration, because the slope of a position versus time graph gives you position over time, which is velocity, and acceleration over time gives you acceleration. Sorry, velocity versus time gives you acceleration. So positive slope, so the velocity versus time graph is a flat line above the axis, because it's a constant positive velocity, and acceleration is 0 because it's moving at a constant velocity. Object at constant negative velocity, it's a line with a negative slope in a position versus time graph. Because of the negative slope, the constant velocity is at negative velocity below the axis, and acceleration is 0, so the line cuts through the axis. There are 3 ways you can express constant positive acceleration. That is with a curve going up like that, which means that the slope, which begins at 0, becomes more and more steeper. It becomes more positive. So it's a diagonal in velocity versus time graph going, with a positive slope. And acceleration is a flat line above the axis because it's a constant positive acceleration. You can also express it as a curve getting less steep on its way down. That represents an object going in the negative direction but slowing down. If you're going in the negative direction and you are slowing down, that means your acceleration is positive. So we start off with negative slope, then we get to zero slope. So that means the velocity goes from negative to zero, the diagonal with a positive slope, and acceleration is above the axis. And it's a flat line because it's a positive constant of acceleration. And then you also have a quadratic curve, which is also a positive acceleration. That means that, um, well, we start off with a negative slope in the beginning. It becomes zero in the middle and then becomes more positive afterwards. So negative slope, zero, and then positive slope. So that means the velocity versus time graph would be a diagonal with a positive slope going from negative to positive, cutting in zero in the middle, and acceleration is a flat line above the axis. There's also three ways you can express constant negative acceleration. One example is something being dropped. So the slope here is zero, and then it becomes more negative on its way down. So you start off with zero velocity and then it becomes negative. So the velocity versus time graph is a diagonal with a negative slope, and acceleration is a flat line below the axis. Now, another way you can express negative constant acceleration is with an object moving up, and slowing down, and reaching zero velocity at the top of its path. Or in other words, an object moving forwards and slowing down, that means acceleration is negative, right? So I'm just making sure here everything's correct. So now velocity versus time graph, it starts out with positive velocity, then it gets to zero. It's a diagonal with negative slope, and there's an acceleration, a flat line below the axis because that's the negative acceleration. And then we have the entire projectile motion where an object goes up and it comes back down at the top velocity zero only if the horizontal velocity is also zero since the start. Because when you launch something at an angle, the velocity at the top will not be zero. The vertical velocity will be zero, but not the horizontal velocity. But in this case, let's assume we're shooting something straight up, launching something straight up. We start off with positive slope, then zero, and then negative. You have the diagonal with the negative slope for velocity versus time graph. And then the acceleration versus time graph is a diagonal. No, it's a flat line below the axis. So you have a way to express motion with graphs, with because graphs become a meaningful way to describe what's going on. For many years, algebra was taught without graphing. Um, Linear equations, quadratic equations, cubic equations were investigated and explored without graphing. The Cartesian coordinate system, created by René Descartes, the French mathematician philosopher, is indeed very useful for us to map the coordinates of the changes in motion and what is going on to the object. So um, we create mathematics for convenience so we can describe the universe in a better way so that we can make predictions for the future and so that we can build our technology. So this was the first video on Xhyn, kinematics, and motion graphs. Thanks for watching.